Traditional blockchains function as static digital ledgers, effectively flat spreadsheets recording transactions. Ethereum expands this into a dynamic, decentralized execution environment. Ethereum operates as an open-source, globally distributed computer. Its primary purpose is to execute programmable smart contracts across thousands of machines simultaneously. The core of this operation is the Ethereum Virtual Machine, or EVM. This is the execution engine that actually processes the code, ensuring every node on the network arrives at the exact same result. To see how this world computer sustains itself without a central server, we will deconstruct it into three foundational layers: the physical blockchain network, the execution engine itself, and the crypto-economic security model that keeps it all running honestly. Transitioning from a ledger model to a distributed state machine is the technical foundation for running decentralized applications without relying on centralized servers. We start at the physical bedrock, the network. This is a globally distributed collection of peer-to-peer computers, called nodes. Their collective job is to maintain and agree upon the current state of the system. These nodes organize data into a block. Stripping away the financial connotations, a block is strictly a data container. It holds a batch of transactions and a set of structural metadata. Vital metadata is kept in the block header: timestamp, Merkle root, nonce, and the previous hash. This hash mathematically locks the current block to the data state of the preceding block. Altering data instantly changes the hash, breaking the link and invalidating all subsequent blocks. The peer-to-peer nodes continuously validate these cryptographic links. Through a consensus mechanism known as proof of stake, they agree on which chain is the valid, uncorrupted version of history. This base layer ensures chronological immutability. It creates a tamper-proof foundation, ensuring that when we run code on top of it, the underlying record cannot be quietly rewritten. With a secure data layer established, we move up to the active computation layer. This is where the Ethereum Virtual Machine takes over. The EVM is a deterministic, Turing-complete sandbox environment. Every node on the Ethereum network must maintain a perfectly synchronized copy of it to execute smart contracts and update the global state. To give instructions to the EVM, developers write in Solidity. It is a contract-oriented, statically typed programming language designed specifically to map human-readable logic onto the blockchain. This flowchart tracks how logic is executed. Human-readable Solidity source code is compiled into machine-readable bytecode, then fed directly into the EVM. Once processed, the execution results in a permanent update to the global blockchain state. Running untrusted, anonymous code on a global network carries massive risk. The EVM operates as a strict sandbox, isolating the executing code from the rest of the node's host computer to prevent malicious interference. By combining isolated computation with deterministic results, the EVM guarantees predictable, platform-independent execution. This is the mechanical basis that allows two strangers to create a trustless, automated agreement. The EVM does not run autonomously. It requires an external trigger to begin computation. That trigger comes from the input layer. Users interact with this layer using wallets. A common misconception is that a crypto wallet stores digital coins. It does not. A wallet is simply a computing metaphor, a piece of software that generates and stores cryptographic key pairs. This derivation path uses elliptic curve cryptography. A highly secure private key mathematically generates a public key. That public key is then hashed to derive a specific Ethereum address, establishing a unique identity on the network. With an identity established, a user can initiate a transaction. This is the sole authorized mechanism for altering the state of the Ethereum blockchain. Looking at a transaction object, we see a structured data packet containing sender and receiver addresses, a nonce, transferred value, gas limits, smart contract payload, and the signature field. By signing this with a private key, the sender cryptographically proves authorization, guaranteeing authentication and non-repudiation. Because transactions are the only mechanism to trigger EVM computation, public key cryptography provides the mathematical authorization required for every global state change. A Turing-complete system, which can theoretically run any computation, introduces a severe vulnerability. A malicious user could intentionally deploy an infinite loop, spamming the nodes and halting the entire global network. The native cryptocurrency Ether was designed to solve this exact problem. Ether functions as a utility commodity, computational fuel,
known as gas, that must be paid to the network for every operation the EVM performs. If a script hits an infinite loop, it simply runs out of gas and stops. To calculate these costs with extreme precision, Ethereum breaks Ether down into smaller mathematical denominations. Values are calculated in Wei, while gas is priced in Gwei. This fuel requirement is part of cryptoeconomics, the deliberate intersection of cryptography, economic incentives, and game theory. Nodes validating transactions honestly are rewarded with Ether. If a validator approves fraudulent data, the network executes slashing, destroying their staked funds. By aligning these forces, cryptoeconomics solves the decentralized trust problem. It removes the need for human oversight by making honest behavior the only mathematically and economically profitable choice. Bringing these components together forms the complete architectural stack. The transaction originates via a wallet, pays computational gas in Ether, is broadcast to the network, and processed by the EVM. Tracking this change from signature to block confirmation proves how seamlessly these layers interact. The system remains stable through a precise division of labor. Cryptography ensures integrity of the data, economics drives network consensus, and the EVM provides the decentralized computational logic. This syllabus document highlights standard course outcomes for decentralized computing. It shows that evaluating the interplay between the EVM, smart contracts, and the underlying infrastructure is the primary academic objective of studying these systems. Understanding the machine's architecture is a prerequisite for building for it. Mastering these primitives is the essential first step before writing decentralized application code.